welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am from Department of Computer Science, Aryabat College, University of Delhi. So we are going through a lecture series of operating system concepts, and in our previous lecture we were studying process synchronization, and within the topic of process synchronization we have seen what is process synchronization and what is its importance as far as threads are concerned, or as far as the normal operating system processes are concerned. And then we have also seen the elements or section of a program, and we have understood about the race condition. So with a quick kind of recap of those concepts, we will be going through more into details of process synchronization, and this time we will be talking about more detail into the critical section and the solutions of this process synchronization, or what all conditions should a solution should satisfy. Again, welcome back to this process synchronization, the second lecture in this process synchronization. Till this point we have seen 4 sections of an element of a program, which are entry section, critical section, exit section and the remainder section, as shown on the screen. So this is basically entry section, as the name indicates, when a process is trying to take entry inside the critical section. Critical section is something which is kind of simultaneously being shared by all the we can say which cannot be simultaneously being shared by more than one process. Then you have an exit section, and whatever that is not being categorized inside the entry, critical or exit section will comes under the remainder section. Now with all these elements, what is happening here is there could be a race condition. So race condition is a situation in which we can say several processes access and manipulate the same shared data concurrently, and the outcome of the execution will depends on the particular order in which the access take place. So for example, 3 processes accessing the same piece of data, if they are kind of getting executed in a sequence of, let's say, P1, P2, P3, there is an kind of we can say the result is X, and if the sequence is P2, P1, P3, the result is Y, or on the other way around, if the sequence is P3, P2 and P1, the result is Z. So basically what is happening here is outcome of execution is going to depend on the order in which the access takes place, and this situation we have seen that this is what you called is the race condition. Now here we have a problem in the form of race condition, and what is required is we need to guard the system against this race condition. So that means we need to ensure that only one process at a time must be manipulating a shared data, and in order to make such a guarantee we require that the process should be synchronized in some or the other way. So basically we have a race condition in which processes are trying to race against one another in order to establish their outcome, or in order to show that their outcome is correct. And in order to guard against this race condition, we need to synchronize these processes. And what kind of synchronization is expected here is that we need to ensure that only one process at a time can be manipulating a particular shared resources. So this kind of solution is required, and this kind of solution comes from the critical section, as we have already seen that critical section is a is something when a process is executing a critical section, the shared data or the data which is common should not be shared at that particular point of time by any other process. So we can say in order to establish a solution to the race condition, it can be done using the critical section in an appropriate manner. That means by treating the critical section as a section that can be accessed by only single process at a time, and this kind of section is also known as an atomic section. So, I repeat that in order to provide a solution to the race condition, we need to ensure that the critical section is something which can be accessed by only one single process at a time. And with this establishment, let us try to drill down into one problem which is known as the critical section problem. First of all, we will see what is this critical section problem, and then we will try to figure out the solution also. So, we have various processes like P0, P1, P2, P3 till Pn minus 1, and the system is having all these n processes, and each process is having some segment of code. So, that segment of code we are calling that as the critical section of the process, and within that critical section what is expected out of this process is, that is, it may be changing some common variables, it is updating a table, or it is writing a file, and so on. That means it is accessing all the common data which is shared, and it is not only accessing that shared data, we are also expecting a modification here. So, when one process is executing in its critical section, no other process is allowed to execute in its critical section. So, for example, within three processes, one process is undergoing through its own critical section. So, if P1 is undergoing through its critical section, and if the demand comes from P2 and P3 to enter into the critical section, that demand should not be fulfilled. That means when one process is executing its critical section, no other process is allowed to execute its critical section by till the time the first one is in the critical section. That means no two processes are executing in their critical section at the same point of time, let us say t. At a similar point of time t, only one process can execute in their critical section. So, this was the problem of this is the problem which is which can we will be using in order to stop the race condition, or in order to kind of we can say guard against our system, against the race condition. Now, coming to what could be the solution of this critical section problem, or how are we going to use that solution, how are we going to establish that only one process is allowed to enter into its critical section. So, basically critical section problem is about designing a protocol that all these processes can use to cooperate, which is the protocol ensures that the process must request permission to enter its critical section. So, once a process is being given the process permission to enter its critical section, no other process will be allowed to enter its critical section unless the first one comes out of its critical section. And the section of the code which is implementing this request will be the entry section, and the critical section may be followed by an exit section, and whatever doesn't comes inside all these three sections is your remainder section. That is what we have already seen. So, one is a critical section. So, the idea here is before entering into critical section, some kind of permission is required, and that permission implementation happens inside the entry section. That is the code of implementing that request for permission happens inside the entry section. Then it is followed by the critical section, which in turn is followed by the exit section. Now, a part of code that can only be accessed by a single process at any moment is called its critical section. That means when there are many processes, there are many programs which want to access and change a single shared data. Only one process will be allowed to change that particular data at any given moment. The other processes will have to wait until that data is free to be used. So, that means if one process is entering into its critical section, no other process is allowed to enter into the critical section unless the first one is coming out, because in critical section it is going to, we can say, update the tables or write on a kind of shared data. So, only one process will be allowed to change any kind of shared data at a given point of time. Now, how are we going to handle this programmatically when we talk about? So, there are many functions as far as Linux systems are concerned, or we can say there are many system calls. So, one is the wait function, which handles the entry to the critical section. So, if one process is already in its critical section, other will be allowed to, or other will be other will be made to wait, while the signal function handles the exit from the critical section. So, if one process is getting entry, the wait signal will be there and a wait function will be executed, while the signal function handles the exit from the critical section. That means a process, when it is coming out from the critical section, it is going to we can say execute the signal function, which will signal other processes that now the critical section is we can say free or unallotted. Now, critical section is something which is, we can say, it's a kind of bottleneck when we talk about process synchronization. But even if we remove the critical section, we cannot guarantee the consistency of the end outcome after all processes are done with their execution simultaneously. That means even if we remove the critical section, the consistency of the end outcome is not guaranteed. And what is this end outcome? This end outcome is the output after all the processes finish executing simultaneously. So, we have understood the problem of critical section. In the previous lecture, we have also seen the race condition, which we have recapped into this. Now, we will be talking towards the solution, we can say. So, we have established race condition, then we have seen the critical section problem, and now we are moving towards the solution of the critical section problem. What all will be the solution, that we will be talking very soon. But before going into, or before jumping on to the exact solution, let us try to understand what are the requirements that any solution to the critical section problem must satisfy. So, basically a solution to the critical section must satisfy three requirements. One is mutual exclusion, another one is the progress, and the third one is the bounded waiting. I repeat, a solution to the critical section problem, whatever solution it is going to happen, that solution must satisfy three requirements as written below. One is the mutual exclusion, the next one is the progress, and the third one is the bounded waiting. Now, let us try to understand these three requirements one at a time, and after that we will be moving towards the particular solutions which are satisfying these three requirements. So, first let us try to understand mutual exclusion. So, mutual exclusion, as the name indicates, it cannot be we can say accessed, or it cannot be implemented mutually. That means mutual behavior is excluded here. So, when a process is running in the critical section, no other process should be allowed to run in that critical section at that time. So, if one process is already in the critical section, it is we can say the section is freezed, and no other process will be allowed to enter into that critical section for that time being, the first process is using it. And why? Because critical section is a kind of, we can say, section of the program in which all the updation of the tables, writing on the files, manipulating the values of the variables is is happening over there. So if one process is in the critical section, no other will be allowed to go into that critical section at that point of time, and this can be understood with the help of this figure. So if you can see it here on there is a process P1 which is accessing a critical section. That means it is kind of manipulating some shared data, and that too in a write mode. We can say manipulation is actually in the write mode. It is not only accessing, it is also manipulating. While if you can see in the figure, other processes which are process P2, P3 and P4 are waiting outside, and they are not allowed to enter inside the critical section even if they demand so. That means they need to wait. So this is, we can say, a correct implementation of or a correct scenario in which we can understand mutual exclusion. Another idea is what is wrong here, what should not be there. So let us say there is a critical section, and within that critical section we have multiple processes, let us say process P1, P2, P3, P4, all accessing this critical section simultaneously at the same point of time is something which is not allowed. What is allowed here is critical section will be executed or will be, we can say, kind of implemented by one process at a time, and other processes like P2, P3 and P4 will be waiting till this process P1 is inside the critical section. So simultaneous kind of, we can say, execution of this critical section code is not allowed. So this is what you call mutual exclusion. So this mutual inclusion which is given on this slide is not allowed. What is allowed is this, which is mutual exclusion. The second property is termed as progress. So now let us say there are kind of three processes which are entering outside the critical section, and one process, as we have seen in the previous figure, is inside the critical section. The scenario is perfect fine. But what if the kind of, we can say, the process which is inside the critical section is making no progress? No progress, that means no process is if there is a process and it is still inside the critical section, it is not making any progress, that is also something which is discouraged, which is not allowed. So if no process is still in the critical section and other processes are waiting outside the critical section to execute, then after a particular point of time or after a particular signal, one of the process or one of the threads must be allowed to enter into the critical section. That means it is something not like that. The process is inside the critical section and it is not making any progress. That behavior is not kind of acceptable. If after some threshold of or some point, if the process is still not making any progress, then the threads or the processes which are waiting outside, one of them must be permitted to enter inside the critical section. Now here is going to be a very kind of important thing, that who is going to enter into the critical section. So this decision will be taken by all those processes which are not executing in the remainder section. The processes which are in the remainder section will not participate inside the which will not participate for the decision of which process will enter the critical section, and this decision will only be taken by these processes which are not executing in the remainder section. So either they are in the entry section or they are in the exit section. So this decision will be taken by all those processes, not by the processes which are in the remainder section. And the second we can say the requirement of a solution is progress. That means the process which is inside the critical section must make a progress, otherwise some other process or some other thread is going to enter into that particular critical section, and then the things will proceed. So, out of 3 we have seen 2. One is mutual exclusion. If a particular process is executing inside the critical section, no other process is going to allowed into it. Then the second is progress. That means one cannot catch the or one cannot catch the hold of the critical section, we can say endlessly, because this is going to generate the third situation, which is of starvation. So what we what we intend to have is no starvation as the third requirement of our solution to the critical section problem. So the first requirement was mutual exclusion, then we have progress, requirement of progress, and the third requirement is no starvation. So starvation here means keeping a process waiting forever to access the critical section, and that process is not going to get a chance. So that this is the situation of starvation. That means a process is waiting for entry into the critical section or waiting for its critical section, and it is kept waiting for the critical section, it is not getting it. And the condition of no starvation is also known as bounded waiting. So as the bounded waiting, as the name suggests, that waiting should be bounded by time. You cannot keep some of the processes waiting endlessly. So a process should not wait forever to enter inside the critical section. So whenever a process submits a request to access its critical section, and this is going to happen inside the entry section, then after submission of its request to enter into its critical section, there should be a limit or there should be a bound, which is the number of other processes that are allowed to access the critical section before it. So for example, if one process, let's say Pn, is submitting its request to access its critical section, then definitely there will be a bound, let's say x number, and this x should be finite obviously. This x number of processes will enter before you, and after these x number of processes you will be getting entry into the critical section. That insurance or that assurance process Pn must be having. That means whenever a process is submitting a request to access its critical section, there should be a limit or there should be a bound, which is nothing but the number of processes that are going to get the critical section before it. And after this bound is reached, this process should be allowed to access the critical section. That means Pn as promised is going to access the critical section after x after x number of processes, because now that bound is reached and the process should be allowed to access the critical section. Now in after these 3, one is mutual exclusion, another one is progress, and the third one is no starvation or the bounded waiting. We have seen 3 requirements, or all these 3 requirements must be satisfied by any solution which is providing the guard against the critical section problem, or which is the solution of the critical section problem. Now with these requirements, let us try to explore one particular concept of lock variable, which is very important in order to we can say in order to ensure the solution of critical section problem, or we can say this lock variable is the simplest synchronization mechanism, and this is nothing but a software mechanism which can be implemented by a user, or this is a software mechanism implemented in the user mode. That is, This is a busy waiting solution which can be used for more than 2 processes. What is happening in this mechanism is there is a variable known as lock variable. This lock variable is used with 2 possible values. One is either 0, another one is the value 1. Lock value 0 means the critical section is vacant, while the lock value 1 means that the critical section is occupied. So, a process which wants to get into the critical section first need to check the value of the lock variable. If it is 0, that means the critical section is vacant and the process can get inside the critical section. But when the value of lock is 1, if the value of lock is 0, it can enter. The value of lock is 1, it cannot enter. But one thing which is to be ensured it that if the value is 0, then just as the process is getting entry into the critical section, the value of lock must be set as 1, otherwise the process need to wait. So, if the value is 0, that means the critical section is vacant and it can get the entry. After getting the entry, or with the entry, we can say it is going to set the value of lock as 1, and here is a pseudocode of this mechanism. So, let us say there is an entry section as the step 1, and this entry section will we can have it while lock not equals to 0. Whenever you have lock equals to 0, that means now your critical section is vacant, then the value of lock will be set equals to 1. That means the critical section is now occupied as lock is having 1. And after getting one process into the exit section, that means critical section kind of code we can say is over now, the lock is again set to 0 by that particular process. So, basically the initial value of lock is 0. The process which needs to get into the critical section enters into the entry section and checks the condition provided in the while loop. The process will wait infinitely, we can say, until the value of lock is 1. Since at the very first time the critical section is vacant, hence the process will enter the critical section by setting the lock variable as 1. So, other processes which are trying to get into the critical section at the same time, if they are encountering the value of lock variable as 1, they must wait. And when the process which is done with its critical section exit from it, then the exit then in the exit section it is going to reassign the value of lock as 0. So, in this lecture, let us try to summarize. We have seen we have started with the recap of sections of program, and then we have seen the critical section problem and its solution. Here is a list of references. Thank you for the patient hearing. Hope you have enjoyed the lecture.